Alright, welcome back. I thought I'd do a quick video on max and min type problem or application in calculus. Sometimes these are called optimization problems also. So let's just jump right into it. It says construct a window in the shape of a semicircle over a rectangle. So you always want to draw a picture that represents kind of what you're trying to find. So here's my window, and I'm still working on my art skills. You've got a semicircle or kind of something that looks like that over a rectangle. If the distance around the outside, so it doesn't explicitly say it, but that's talking about the perimeter. So one of our equations is going to be a perimeter equation. And before we kind of set up our equations, we should probably label what we have. And so you can set up your variables however you'd like. Because this is a vertical length, I'll put a y here. And a lot of times you put an x down here. And you can put an x if you like. But because there's a circle up here, we're going to need some of the equations for a circle. Maybe we want to put this as r and r. And then maybe down here we could think of this bottom length as 2r. It's totally up to you. But because I think we're going to have r in our equation, or at least use the radius, maybe we want to use r. Anyway. So the perimeter is going to be, according to my diagram, it's going to be y plus 2r plus y. So going around this part. And then I need half of the perimeter of a circle. And so the perimeter of a circle, the circumference anyway, is 2 pi r. That's for a whole circle. And I just need half of that circle. So I can say that it's plus pi r. So if I simplify that a little bit, I've got 2y plus 2r plus pi r. Okay. And I also know that perimeter is 12 feet. So I can fill in a 12 here. And I can have 2y plus 2r plus pi r. And with most optimization problems, you need to have two equations. And so if we read further into it, it says, what dimensions will result in the rectangle having the largest possible area? And so my second equation is going to be an area equation for this same scenario. And so the area is going to be the area of the rectangle, which is 2r times y, plus I need the area of, half of a circle. So we have pi r squared would be the area of a circle, but I only want half of that. And so what I now have is two equations connecting the same scenario. And before you ever take the derivative, and in this case, when we want the largest possible area, that means we want to maximize the area. So at some point we're going to need to take a prime. But in order to take a prime, it'd be really convenient if this was in one variable. Meaning I have r and y. Remember, pi is not a variable, it's a number. And I have a r. And so we usually use the second equation to isolate a variable and then substitute it in here to get an equation in one variable. And so let me just at least set that up, and then if you guys want to finish this question at home, you can or something. So if I take my perimeter equation, I've got 12 equals 2y plus 2r plus pi r. And let's just say for 1 second, I'm going to isolate y. And so I could just take 12 minus 2r minus pi r equals 2y. Just move these both to the other side, and divide everything by 2. And what we've got is, 6 minus r minus pi r over 2 equals y. This is a little messier than I expected, but hey, sometimes math is. And so this y, this expression right here, I could rewrite. I have 2r times y plus 1/2 pi r squared. And this expression, 6 minus r, let me switch the colors again. I picked the same exact color, wonderful. This expression goes right here, 6 minus r minus pi r over 2. All right, it looks pretty nasty, but if you actually clean it up a little bit, maybe distribute this in, you get 12r minus 2r squared minus 2 pi, make sure I don't screw this up, r squared over 2 plus 1/2 pi r squared. When you take the derivative, all you have is some power derivatives. Even before you take the derivative, maybe you can simplify some of it. But the goal when you find a prime with respect to r, you're kind of finding dA dr. If you want to see the notation, you'd have a 12 minus 4r minus 2 pi r plus 2 times 1/2, you just have a pi r. And you set it equal to 0. And now you would be in charge of solving for r. So it looks like your answer would have some fraction of pi in it. But when you get that r, that would be the radius that would lead to the maximum area in this scenario. So the hard work is past us. If you'd like to finish it, have at it. Sorry, my voice sounds terrible. A little under the weather, but anyway, have a great day.